or all using are getting the benefit of this microprocessor, which was invented in 1959. Later, 10 years after, 1969, and the ARPANET, or the internet, the modern internet was developed. So this the screens are moving. I could not. Yeah, right. 1969, the ARPANET, or the predecessor of the today's internet, was born in 1969. So, but with this ARPANET, or the today's internet, the millions of people are getting connected. So we could see that most of the technologies which you are getting benefited out of, which shapes our world, are primarily because of some of these inventions which happened 50 to 60 years back. What has created these technologies? It's primarily the engineering community. It's engineering. So all across the world, the engineering community work hard. They are creating new and new technologies on an everyday basis for what they do. Really, they are trying to solve the problems all across the world. Mankind problems are common most of the places. So they are trying to solve problems, and they create solutions. They create a lot of solutions to solve these problems. But my question, the bewildering question, is most of the time you just see, the technologies which have been developed. Are they really useful to mankind? Are they have got the real benefit of, for what reason it has been created to, or what reason the research has really been done? Maybe 20 or 30 years back to that real invention has happened. But not all technologies, I would say that not all technologies during that time was not really bad, or not so having that much bad influence on the mankind. Let us revisit the same time period. There were certain unnoticed technology milestones which happened during that time. Let us see in 1952 what else has happened. 1952, John H. Gibbon, he invented the heart-lung machine, which has saved millions of people who are having the heart failures or heart attacks or heart-related issues. There they were put into the heart-lung machine when a bypass surgery was conducted. So 1952, when Edward Teller made the bomb, at the same time, the John H. Gibbon has invented the heart-lung machine, which was not so noticed or get unnoticed because of many reasons which we don't know. The people get benefit out of it. Millions and millions of people got benefit out of it. What happened in 1959? If you trace back the history, you see that in 1959, William Greatbatch, he invented the pacemaker, which made the beginning of active implantable medical devices. Similarly, in 1969, when the ARPANET and the modern internet happened, a very big innovation discoveries happened called magnetic resonance, where Nobel Prize was given. And with that, Raymond Damadian, he invented the magnetic resonance imaging technology, where you could see inside our human world. You could see inside what is happening inside our body. Many advancements has happened later on in these areas, which ultimately brought the biomedical engineering, which you say. Biomedical engineering is a collection of so many different disciplines, interdisciplinary, you can say. It has got electrical engineering, mechanical engineering, electronics, chemical, signal processing, put into where? Into a biological system, to understand, to diagnose, to treat, to replace the functions of a biological system. And with this biomedical engineering played for last 50 to 60 years, what we have made a lot of implantable devices. We have made different types of devices. First, you can see on the left side is a heart valve. It's a heart valve which replaces the biological valve within our human body. The next is a stent, which is used for wherever you have got a clot, or whenever you have got a kind of ischemia or a myocardial infarction, or in general a heart attack. You may be the patient may be asked to undergo an angiogram and then an angioplasty or then a stenting operation. So this stent goes into your body and then enhance the diameter of the blood vessel and have a continuous blood flow allowed. And another one is an artificial blood vessel. There is a very severe medical condition called aneurysm. In that particular condition, the blood vessel expands than the usual diameter, and it makes something kind of a balloon rupture. All of a sudden, it ruptures, and all the blood goes into internal inside our body. And this is a very life-threatening situation where we have to put an artificial blood vessel. We also have made so many orthopedic and orthotic devices where the knee can be replaced, the shoulder can be replaced, or even the tooth need a fixation. All those devices are implantable devices. These devices, there is a commonality. The devices does not need an external energy for its operation. Because of that, it is called a passive device. So these are all passive implantable devices. You don't need to provide electrical energy or a mechanical energy or any chemical energy for its function, for its activity to happen. But what are the various challenges which made it so complex in its manufacturing, in its development? Because it's critically placed. Critically placed means the heart valve need to be placed exactly over the biological valve which is damaged. Otherwise, it won't function. So you need to have the valve which is kept within the rib, which is kept within the heart. The heart itself is kept within the pericardium. The whole thing is kept within the rib cage, which is completely enclosed by a tissue and skin. So you need to approach into the heart valve and then deploy it. So it is critically placed. Your stent, it is a critically placed because you need to have the clot to be identified first and then introduce the stent into that particular location. Then it needs extremely high surface finish. Otherwise, what happens? The blood gets clotted over the surface of the material. It needs to be deployed so precisely. Moreover, it should have a prolonged functionality. You cannot put a expiry date onto the functioning of this particular device. You put a stent, you say that 1 year after the stent will not work. No, that is not going to help the patient. So you need to have a prolonged functionality, a long duration. Most of the time, we say for a medical device, the lifetime is actually the life of the patient. So how many years the patient is supposed to live, that many years the medical device also should work. And another important factor, the challenge is it should be maintenance free. That means you cannot open it very often and then clean it or remove the problems on it and repair it and then put it back. So you need to have a maintenance free system. So it's very difficult to attain each and every point which I said right now. But to add to this complexity, another thing is like selection of the material. We don't have so many choices available for making implantable devices. There are only very few selected devices which you can say as a biocompatible. That means which is friendly to our human body environment. So which are those devices? It can be titanium, a special kind of stainless steel, nickel titanium alloy called nitinol, cobalt chromium, certain polymers like polycarbonate, polyurethane, Delrin, Teflon. So very specific choices of material is present for the manufacturing and development of implantable devices. You would have seen certain other devices also in use right now. Something like the heart lung machine, which I have said in the beginning, the dialysis machine, the blood bag as such, where you store the blood, the ventilators or the anesthetic machines, the defibrillators. This you are studying in your curriculum. You are understanding the function. You would have seen it in the hospitals, how it works and all. Now, another one is for medical diagnostics. Most of the treatment, no, before that you need to understand what exactly need to be treated and what is the disease condition. For that, there are a lot of biomedical equipments, a lot of instruments and sensors currently available, which you can collectively call as medical diagnostic devices. So there you can have an ECG machine. On the left top corner is an ECG machine. You can have an ultrasound machine, a CT machine, and an MRI machine, or an EEG machine, which monitors the functioning of a brain. Or it can be a flow measuring device, or it can be so simple and commonly used device like a blood pressure monitor, a glucose monitor, where only a prick of and a small drop of blood is sufficient. You can also, we would have seen, or most of the people would have bought and used it at home, a pulse oximeter, which is also a medical diagnostic devices, which needs sometimes electrical energy or a battery operated or standalone or a tabletop models. Or so many different configurations and varieties are available, which finally judges from certain signals taken from the body, and the clinician may be able to interpret the output and say this is the disease. So once you have identified what is a disease, how do you treat it? There are a lot of devices now for the treatment as well. On the left hand top corner is a fluoroscopy machine, which is available in a specific room called cath lab room, where we call it as catheter laboratory. So in the catheter laboratory, we identify the position of a clot or position of a plaque in the coronary arteries of the heart, and then to precisely to that location we introduce a catheter and then a stent or a balloon, and then remove the clot. So this needs live streaming, a live identification of the position of the stent where it is to put. So we use X-rays, continuous pulses of X-rays, and then live streaming to deploy the stent into the exact location. So this is a catheter laboratory, and if it is a cancer, you need to have radiations, certain radiations into pinpoint into the cancer cells and then burn it off. So you need the radiotherapy equipments. Most modern hospitals now have got surgery being assisted by clinicians who are kept, or surgeons who are placed in a remote place, in a faraway place. So now it is possible even in Kerala that you can have a robotic surgery unit is available in certain hospitals where the robot handles the surgery and the clinician may be very far off, maybe in another continent. Even in the same location, a clinician can use the same robot, but it manipulates in such a way that all the tremors, accuracy, and everything will get improved when you use a robotic surgery. And the last one is a LASIK treatment, where we use another energy source, which is actually the laser. So in all these things, we use different types of energy sources. One is an X-ray, another one is gamma, and another one is precise movement of electrical energy is used into different motors, and other one is laser. So all these devices, either treatment or diagnostic or replacement or implantable, if it is passive, all those devices try to solve a problem which is persisting in a human body. But what if the whole organ is problematic? What if the whole function of the organ need to be removed and then have to have a replacement, have to have a substitute? Then you need certain devices to be put inside the body, which is really active in nature. So for example, your heart, it's an active device because heart takes energy from the body and it keeps on pulsating. Your lungs is it's an active device because the lungs expand and contract, thereby taking the air inside and then get the oxygen into the blood vessel. You take the kidney, you take liver, you take brain. No, it needs energy. If you are not taking food for a long time, no, your brain becomes dizzy, you not be able to concentrate. And after a few days, if you're not taking food for a long time, for some days altogether, you may become unconscious sometimes because you're not getting enough blood supply, you're not getting enough energy for the brain to function. So all these internal, most of the devices, not devices, more of the organs, natural organs are really active. So what you need, sometimes you need the artificial organs which are kept in your body for replacing or substituting that natural organ need to be active also in nature. It should take energy and then do its function. Let us have a recap of what are those natural organs and what are its specifications, or what are its real challenge in doing so. So if you need to engineer the human organs, you need to know what are the complexities, you need to know what are its real issues in doing it, why we are not able to do it so easily. Okay, you might have seen about the functions of a heart in your anatomy textbook, maybe in a biology textbook, or later in your biomedical engineering courses. But one thing which we forget is it's like long duration activity. Now, your heart actually beats more than 3.8 crores every year. And if you take a lifetime of 60 years, it's something like 2.5 billion times. So 1 billion is 100 crores. So 2.5 into 100 crores times. That many times your heart has to beat till you attain 60 years. So anytime if a beat stops, anytime the heart starts like weakened, I'm busy for another action, I'm not able to beat now, then you get the cardiac arrest, then you get a myocardial infarction, you get a heart failure. So that's a life-threatening situation. Another few minutes you will collapse. Think about the situation of a blood vessel. The heart is a source of the movement of the blood, now through which the blood moves, the blood vessel. So see the complexity of the blood vessel there. The large blood vessel which comes out of the heart, it's the aorta, splits into millions and millions and millions of small arteries called capillaries, and sometimes it gives blood into the real source, which is the coronary artery, which gives blood into the heart itself. And the total length is estimated to be more than 60,000 miles. That much total length of blood vessel. Anywhere there can be a traffic block, anywhere there can be a small disruption of the flow, there can be a small clot formed. If that clot is formed on a particular place which is giving blood into an organ, which is giving blood into a very critical function of our human body, then it is a life-threatening situation. So it's very, 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 very important to understand all these things. Think about our brain. More than 100 billion neurons. If a neuron misfires, you can see it very evidently on your face, on your body, that you get some malfunction of your normal behavior, normal function. So these 100 billion neurons fire in such a way that your normal behavior or normal functioning of all the internal organs happen. Similarly, for any other device, let us take lungs. Here you have got multiple chambers. You have got this is one of the largest organ, very large size. It could take 5 to 8 liters of air every minute. So it's such a large volume available inside, and it takes 20 times a kind of a minute, and millions of times. It's a very, very similar to that of the heart. It operates without having any leak, without having any rupture. It keeps on expanding and contracting. You consider about a filter which is present in our body, which are the kidneys. So if you make a comparison with the filter which filters the impurities from the water, which is available in every kitchen nowadays, you need to replace the cartridge once in a year or once in 2 years. What about your kidney? Are you replacing it? No. So the kidneys, the function is to filter the blood, something like 100 ml per minute. It is filtering. It's a filtration rate, an approximate figure, but it is doing very without any problem for most of the people around us. And if there is any small issue, then we call it as a kidney failure, and then based upon the degree of failure, we go for up to the max a dialysis. Okay, now what has we made for engineering these human organs? Very little. Even with the latest technology, you have got all those technologies which is invented from 1950s, the most prominent of the microprocessors, the technologies on enabling the internet and all those things. We could not have a complete 100% replacement of functions of these major devices within our body. Is not achieved by mankind. So it's very important to have these devices being developed. These organs functions need to be mimicked or replaced or substituted with artificial devices. And since it has to take energy, then we can call it as an active implantable medical device. Let us take why it is so important. The reasons are, if you consider the top 10 global chronic diseases by prevalence, then the first one would be heart diseases. The second one would be, nowadays, because of the infection is so prominent, there is a higher trend on the infectious diseases as well. Otherwise, you have got neurological disorders, then diabetes, cardiovascular diseases, musculoskeletal diseases, pain because of cancer, are all the major in the list of top 10 global chronic diseases. These all needs the replacement or substitution of functions of the organ. So in this case, we need the active implantable medical devices which takes up the function of these organs. If you consider the maintaining the balance of our brain, then a neurostimulator is required. If you want to have an auditory replacement function, then you need a cochlear implant. Similarly, if you want to have your eyes with a replacement function, then you need an ophthalmic device, artificial eyes and all. If you want your stomach, because coming down, you have your heart. The heart need to be replaced with a real similar functioning medical device. You need a ventricular assisted device or a total artificial heart. Then if your stomach need to be because stomach has got some movement, the intestine has got some movement, so all those things need stimulation of the neurons surrounding it. You need gastric stimulators. Your pancreas produces insulin. So if you want to have your glucose being monitored, you can have diagnostic devices for glucose monitors. But what if you want to deliver insulin inside, if your pancreas is not working for different types of diabetes, then you need infusion pumps which can be implanted within the body. What if you want your muscles need to be twitched, the muscles need to be stimulated, you need generators of electrical pulses which can stimulate the movement of the muscles. So all these devices comes under the active implantable medical devices, which is the topic of our discussion today, which primarily needs an energy source. Most of the cases, this energy source comes from an implantable battery. So all these devices has got an implantable battery inside, and this battery is very miniature, and it is encapsulated into a titanium frame or a metal frame. And as you can see here, it goes inside into a very small footprint which goes inside the body and replaces the function of the. So we will take one by one. I may not be able to explain to you all the devices in a single talk. So I will take a few of the devices, and those devices which we are also working on the last 10 years time period. We have made significant improvement on the development. Some of the devices have gone into the technology development, into the end stage of technology development, where the technology is transferred to industries, and industries are fastly trying to commercialize it, because the need of the hour is to develop most of these devices in the country, because our population is exploding. We are going to be the #1 in population among all the countries of the world. So we have to have all these devices developed within the body to cater to our aging as well as ailing population. So let us see one by one. So which one we should take first? So for that, a scenario need to be understood. The statistics says that the world's leading causes of death is primarily due to heart diseases. So then comes a stroke. So mostly two things comes, like one is a heart disease and then the brain diseases. So we will take in that order. So we will see what are the active implantable medical devices which can replace the function of a heart. Similarly, later on, we will see what are those devices which can be used to replace the function of the neurons. Where the neuronal activity can be stimulated, where it can be on the brain or on other parts. Later, we will come down based on the priority. We'll come down to other devices like other ailments like cancer or movement related problems like that. So as you can see here, the most major problem which is kind of attacking the population all across the world is a heart failure. So what is a heart failure? It's a chronic progressive condition when the heart muscle is unable to pump enough blood. And the cardiac arrest is another problem where your heart suddenly stops. So in both these conditions, the heart is not functioning. Because of that, you are not getting enough supply and you may suddenly collapse. Okay. More than 8 to 10 million people in India suffer from heart failure, and it is very high in urban, and it's like maybe half is there in the rural. So 10% of the population in urban is having this particular problem. Okay. Now, currently, what are the advanced cardiac failure therapies? What is currently available? Now, we have to have a look on what is currently available. So first is medical, pharmacological treatment. There you go and see a doctor. They understand based on so many diagnostics. They understand what is the current condition of your heart, and then certain medications will be prescribed. So what really these medicines do? It improves the symptoms, but will not change the patient mortality, because you are not really solving the problem. You are only kind of evading the criticality of the problem. You are only evading the progress of the problem into a much bigger issues, but still it is progressing in a smaller way. But if the doctor identified, the clinician identified that it has got into a larger problem and you need surgery, then the another phase of this cardiac treatment is a surgical replacement or a surgical removal or a surgical correction. So what are those which comes under the surgical therapy? Angioplasty, bypass. CABG means bypass therapies. Valve repair. You need to change the valve with a different valve. What exactly the surgical things do? You will be relieving the symptoms, but may not affect the propagation of the basic process. That means still the problem will be there, but you can relieve most of the symptoms. Your pain may be addressed, your progression may be slightly reduced, but still the basic problem still remaining there. One of the best available therapy for advanced cardiac failure is replacement, which means your heart need to be replaced with another heart. So the heart transplantation is the best option for this kind of advanced cardiac failure. But all across the world, at any point of time, that then you need a donor to get this heart, and you need the donated heart to be placed in the recipient's location, the heart location. But you need a donor first. So in any point of time, millions of people want this heart transplantation to happen because there are millions of people who suffer from the heart failure. But at any point of time, less than 5,000 donors will be available all across the world. And you would have seen the issues by certain films have come out of it. You might have observed in that films that how difficult it is to get this heart from different locations into the location of the recipient. It's very difficult. You need to have a different departments working together to manage the logistics of getting a heart from one place to another place. So is there any other option available? Yes, now there is an option available in advanced countries. That option is called substitution. So substitution means you substitute the function of the heart. What is the function of the heart? The pumping of the blood. You substitute the function of the heart by using mechanical circulatory support systems, which are certain systems which is mechanical or electromechanical in nature, and it pumps the blood throughout the body. Whereas you can have a rest to the heart. The moment the baby born till the person dies, the heart is not at rest. But you take any other organ of a body, if you are under medication, if you have some ailment, the doctor prescribes a medication, and also you need rest. Whereas a heart failure patient, you take the medication, but there is no rest for the heart. So if you have this kind of therapy, substitution therapy, then what you are intending to do is having a medication as well, plus rest to the heart. There is a very large chance for the heart to come back. That's one thing. And if the heart is not coming back, then the device will take care of the rest of the living of the patient. The technology is available, but what is the problem here? The problem is this know-how, this knowledge, this is an intellectual property. It's available only in certain elite countries like America, Germany, Russia, and Japan. So these 4 countries have the knowledge of developing a heart-assisted device which will take the function of the heart and then do it. It is very limited in supply because of the exorbitant cost. So what is the cost? To get a device, a similar device in India, the cost is more than 1 crore per device. As per the latest registry, you could see that even though with the high cost in developed countries, more than 1,500 patients per year, it is growing in numbers, those people who are getting this particular treatment option. So why can't we have it in India? Definitely we should have it in India. So that is the reason why maybe this talk itself will help. And also we have been working for the last 10 years in developing this similar devices. So let us see in detail what is this device and the technology which is present in this device. So it's an artificial heart to assist the failing ventricle. I'm not going into what is a ventricle, what is an atrium, and what is an anatomy of the heart. I assume that you people know it. So a ventricle are the chambers which pumps the blood from the heart. So there are 2 ventricles. One is called the left ventricle and the other one is right ventricle. The valves actually separate the ventricle from the atrium. By opening and closing, you are getting a unidirectional flow of the blood from the heart. So if you are assisting the function of the left ventricle, then this artificial heart can be called as a left ventricular assist device. If you are assisting the functions of the right ventricle, then you can call it as a right ventricular assist device. Sometimes both the ventricles of the heart may have a problem, then you may call it as a biventricular assist device. So why the ventricles are getting problems, why not atriums? Because ventricles has to provide that sufficient pressure to push the blood throughout the body at 100 mm Hg pressure. So this extreme pressure for 2.5 billion times a year up to 60 years of age may weaken the muscles of the ventricle more than the muscles of the atrium, because atriums are not really pushing it to the entire body. It's only pushing into the ventricle. Ventricles are pushing into either into the lungs or into the complete parts of the other organs and the whole body surface. So what you can do for that? You can have an assisted device. So the assisted device works like this. You need to put a puncture on the ventricle apex and a tube connects into the device. The device is a pump, which is an electrically operated device. It has got a motor inside, very miniature. It has got an impeller which rotates. It's similarly a pump which you may be using it in your house or which you are using it in an aquarium. Similar kind of a pump. It's very small, but the complexity is it is used for pumping the blood, which is kept within the body, inside, connected to the heart. The outlet of the pump is connected to the aorta. So what it does effectively, it does bypassing the whole circulatory source, which is the heart. It is actually bypassing the heart internally inside the body. But how do you rotate the pump? How do you give power to the pump? This pump need to be operated by an electrical energy. So for that, a cable is required. The cable comes out of the human body through a small puncture or a small hole in the skin, and then the cable gets connected to a controller. And the controller will have the sufficient memory, sufficient control systems, and all the electronics required for monitoring and controlling the pump activity, and as well as it will have the battery. So this battery may be sufficient to operate for 24 hours, 365 days, as long as the device works, as long as the patient can support it. Okay, so this is the technology currently available as an active implantable medical device for supporting the functions of the heart, even though you are in the end stage of your life and the patient is not your heart is not in a working condition. That time, this device will help the patient to come back to life. This is how a modern technology looks like. You can have the complete view, inside view. The latest technologies have got fully magnetically levitated. That means the rotating structures are not touching anywhere, because the moment it touches, then there will be a scratch. When there is a scratch, there will be material coming out. This material will go into the bloodstream. It can create thrombus or a clot. The clot go into the brain and create a stroke, or it can go to the different other organs and can render the functions of that particular organs. So this particular small demonstration shows how this pump together with the motor are encapsulated into a very small device, and how the blood moves. So the modern left ventricular assist device, their main aim was to reduce the size and the miniaturization in terms of size, overall dimension, as well as the total weight. See, the first similar kind of a device happened in like of 90s. It was Ventry Assist, then HeartMate 1, HeartMate 2, HeartMate 3, HeartWare. So many models have come out of from different advanced countries. And finally, we have come up to a device called HeartMate X, which is so small, which can be kept within the heart itself and does the functions of the heart. But as I said earlier, the major problem is it is available only with allied countries such as USA, Germany, Russia, Japan, and the cost is so high so that it is not being used in India. One or two devices have been used as part of the clinical trials. Otherwise, it's not available in the country. So this has made the scientists of our country to look onto the technology development on how we can make a device within the country at a very small price, so that it is affordable to our layman, an ordinary patient. With that mission, last 6 years, SCTMST is working on developing an artificial heart in the form of a left ventricular assist device. And the last year, we have successfully completed the first few animal trials of this particular technology. We call it as Chitra left ventricular assist device. You can see here a model of that, where a hole will be put on the apex of the ventricle. A dummy heart is shown here, and then with a graft or an artificial blood vessel, it will be connected to the LVAD. So this is the LVAD. The LVAD is made up of titanium. Then it has got an inlet and an outlet. The outlet is connected to the aorta, and the inlet is taken from the ventricle. So whatever blood comes into the ventricle from other parts of the body will be sucked by this device and then push it into the aorta with the sufficient pressure required. We are looking forward to use this device in 3 different configurations. One is called bridge to recovery, another one is called bridge to transplant, another one is called destination therapy. In bridge to recovery, the device will be put on a patient, and we assume the patient can recover with providing rest and medication to the heart. If once that stage is over and if the patient is not recovering, then the same device will be put in for a bridge to transplant. That means we will be opting for a donor heart. If the donor heart is not arriving because of many issues, then we will be looking forward for the next 3rd stage of a configuration called destination therapy, where the same device will be put in the body as long as the patient lives with that. So artificial heart, primarily it is for supporting the ventricle of the failing heart. So the whole system consists of the LVAD, pump, motor, everything together. It has got a controller, it has got multiple batteries and a battery charger. So what are the features which we have incorporated into this LVAD over the last 10 years of development, we have got a hydrodynamic and a magnetic bearing, which means that the rotating parts of these devices are not touching anywhere. It is not having any friction with any of those internal surfaces, so that we are trying to minimize any complications due to thrombosis and the blood damage. So you could see how the impeller, which is a rotating portion of the structure, rotates. So we have got a unique patent for this. So this you can see how it is levitated and it's operated. This work on a complicated magnetic bearing technology, where electromagnets and magnets are kept within the small casing which I have shown earlier, and then it works in such a way that the rotating structures are always levitated and not having any contact with the surface. Now, another important aspect is these are devices which uses electrical energy. You know, any electrical energy produces heat. Sorry, any electrical devices produces heat, but this heat should not be dissipated within the body, because the body temperature will increase. You know that the temperature of our body normally is 37 degrees Celsius. The maximum allowed temperature is like a 40 degrees Celsius or 41 degrees Celsius, beyond which, you know, you will not be able to withstand the temperature. That much of high temperature is 41 degrees Celsius. So you need to have an excessive simulation and testing of your device to understand what is really happening in the LVAD where it is put in the body. So we have done a lot of thermal analysis to understand what is the temperature. You could see the maximum temperature is less than 40 degrees Celsius are allowed with it. And our another feature is that this device communicates with the mobile phone through an application, and all these parameters comes to our mobile phone of the patient as well as to the clinician. In the last few years, we have done a lot of evaluations with the animal. It's very successful. Now we are entering into the second phase of development, where long duration trials we are planning, and the third phase is putting on a human body and then understanding the performance. So in the last 7 to 8 years, what we have achieved, we have made it like extremely small. Indigenous motor has been developed, a brushless DC motor has been developed, a levitation technology has been developed, smart controllers have been developed, CFD simulations and thermal simulations have been done. We could make it extreme with the titanium. Very small pieces have been made and fabricated with titanium with advanced technologies. A lot of testing has been done, and so many numbers have been tested in animals. And recently we have transferred the technology to the largest medical device manufacturer in our country called Merrill, and they are making it in a kind of commercial stage. Production is going to happen in 1 or 2 years time, and later on the clinical trials will happen. So far in all these milestones what we have achieved, we have applied the state-of-the-art technologies and techniques for the design and fabrication, which is completely make in India in-house technology. We could not get, because this is something that is highly protected by the other counterpart countries like America, Russia, Germany, or Japan. They won't give the technology because the cost of the device is so high. They won't give it for free, and you cannot get the device to understand how it. Just you cannot see the device because it will be. There are no patients available in the country where this has been put. So we had to develop everything from the scratch in-house in the laboratory itself. So what is happening next? What are the research which we have to do to make it into the next stage? You have to have so many sensors to be put inside the devices to make it more adaptive and more working towards the real situation. So you need to have a flow rate measurement, you need to have a pressure sensing, and also how do you power the device continuously? You cannot have a cable coming out every time, and then the cable coming out, and then management of the cable, management of the infection, and all those things are very tricky. So we are also looking for the advancements in wireless energy on transferring the energy across the human body, so that there will be a set of coils. So these coils will be powered in such a way that just like nowadays your modern mobile phones are charged, we will be able to charge the device, the LVAD or artificial heart, which is kept much deep inside the body, and then work continuously 24 hours 365 days. But it's very, very challenging. Nowhere in the world has ever made it 100% successful. We are working on towards it. Okay, now coming into the next phase of it. LVAD does the activity of only ventricle, only a small portion of the heart, but it's a very major function. What about if you have the whole heart to be replaced? Then you need the most complex medical device till date been tried out or been researched into, which is a total artificial heart. So the total artificial heart, the research started 1920s onwards, but nowhere in the world it has been 100% successful. Let us have a quick kind of historic perspective of what has really happened in total artificial heart, and then what is the current practice been there, what is in the research phase, how far the entire world has reached into developing a total artificial heart. So the first total artificial heart was developed by Domingo Leotta, and this is a picture of the first total artificial heart. And in 1969, as you know, you should see the year 1969, where the internet was developed. During the same time, another unnoticed technology also started shaping up, which is the total artificial heart. But the first patient who received this total artificial heart only lived for 64 hours, just like 1.5 days. Till that year, from that year onwards, till now, research is happening on improving the survival rate of the patient, the longevity and the survival rate, how far the patient can be supported with this particular device. And the next one came called ABEACOR, where in 2001, this particular device could, you can see the device here, and it looks like a complete heart. This particular device could help a patient survive for 151 days, half a 6 months time, or like 5 months time, 151 days. But this is all made up of plastic and metal and electromagnetics and motors and all those things. It has got kind of wireless energy transfer tried out. It has got multiple implantable batteries. This is very complex, but very small in size. It has to fit into the thoracic cavity. Right. Later, research was done by a French team on improving the survival rate by using biological materials, not the artificial man-made materials, by using biological materials. There, what we have done is pericardial. That means the tissues present inside the human body itself. The pericardium of bovine, that means animal tissues, were used for making the internal structure. Similarly, valves which are taken from animals were also used. So it means everything natural. Most of the things are natural, but certain gears and kind of electronic and electrical things are present to push the blood. But unfortunately, the world's first receiver of this particular heart could only live for 75 days. More than that, it could not support. So that means if you put only all biological systems, you may not be able to make it. So having a higher survival rate and durability. So something more is still the major influencing factor on developing a total artificial heart. So what's the latest? The latest is something like this. You can see a person handing a total artificial heart kept on the hands of a person. There you have a magnetic bearing introduced. You have got a set of motors where brushless DC motors are used, and then the whole structure is so small and it worked. The clinical trial is yet to happen for this particular device, but I assume that this particular device will have a higher longevity and survival rate for the patients. So this shows what are the major technologies currently available in terms of assisting the function of a heart, or completely replacing or substituting the functions of a heart. What next in this particular area? You see the function of a heart, it is beating. So you need to have the beats required. Now you need to produce this beat. So introducing this pulsatile flow to mimic the natural heart rhythm is another challenge faced by the biomedical engineering team all across the world. So you need to have the same pulsatility being created by these artificial devices also. If you could create all these things, I welcome you to see a video of, if it works. Let me see if it works. I don't know if it really works or not. Okay, this is a person who has got the LVAD implanted, artificial heart implanted, but see the physics. He's so superior. He is actually working out on a gym. So right now the technology has matured into this particular level where the LVADs and TH could be used for making a patient live like a normal life, having a most strenuous exercises also possible. Okay, so this is all about one area called the most prominent diseases on the top 10 list, which I have shown, where the active implantable medical devices could really help. Okay, so let us move into another area called movement disorders. So movement disorders, the one which mainly affect the aged people, old aged people. So movement disorders are a group of diseases and syndromes affecting the ability to produce and control bodily movements. You could see how difficult for the aged persons to grab something, move, and all those things. Why is it happening? Because they are having a disorder in their brain. Such disorders are called movement disorders. There can be different types of movement disorders called Parkinson disease. There may be something related to the memory problem, dementia. There may be, essential tremor where the person's hand and all gets shivered all the times, tremors all the time. So these all problems are actually being produced by the misbehavior of the brain. So now earlier we have seen the problems of the heart. Now we are going to see the problems of the brain. So this particular problem can be solved by a magic device, an active implantable medical device. We call it as a magic device because the moment you turn it on, the problems faced by the patient gets solved. So you could see the tremendous impact of this particular new treatment, which has come out from advanced countries on movement disorders. That technology is called deep brain stimulation. So deep brain stimulation means certain parts of the brain are not actually firing properly, and those regions need a stimulation. So here there is a portion in our brain called subthalamus nuclei, which acts like a kind of a relay for an internet. If you say an internet or an intranet in your organization, there will be certain switches kept different places, relays and switches. What they do, they channel the knowledge, they channel the information and data to different networks or to different computers. So your brain is actually different sectors, different segments are there. Your brain has got cognitive, you have got visual, you have got muscle movement control, you have got your involuntary control. Different locations are there, but the sensors are there placed all across the body. So all across the body, the sensors give data, and it will need to be channeled to different the organ controlling centers of our brain. So how do you do that? You need a relay mechanism, and that relay mechanism lies deep inside the brain called and they are called subthalamus nuclei, STN. So this subthalamus nuclei, if it is not working properly or if it misbehaves, then you get this kind of brain disorders like Parkinsonism, dementia, essential tremor, and all those. So almost all the major problems associated with the brain, other than the cancer, are mostly related to this type of neuron transmission or neuron misbehavior. So what you can do for that? There is another active implantable medical device called deep brain stimulator. So this deep brain stimulator involves implanting certain electrodes within the brain deep into this region, and there you provide electrical pulses, extremely small square pulses, small voltage square pulses, very less electrical current. And what it can do, it can solve the problem of this misbehavior of the neurons. So this particular image shows how it works. You have got the subthalamus nuclei. You can see here the yellow colored patches, and your device, which is kept on the shoulder, gives electrical pulses to the subthalamus nuclei, and it really solves the problem. The devices are very small, something like the pacemaker, very small devices. It has got certain leads. These leads are connected to wires, and the wires will ultimately go into the electrodes, and the electrodes are kept deep into the brain. Okay. Understanding the large aging population of our country, SCTMST has done work on developing a deep brain stimulator for our country. So that is called Anuchitra Deep Brain Stimulator System, DBS system. We have done it in collaboration with Baba Atomic Research Center. You can see here, this is a device which SCTMST has developed in the last 5 years time period. You could see that there is a waveform which is generated by this particular device, and this waveform energy, this small electrical pulse energy, is transferred through a cable, and it is transported into an electrode. So this electrode is kept into the patient's deep inside the brain, and it can be monitored by using a mobile phone. So what is present inside this device? This device has got a small battery. It has got a power supply regulators, microcontrollers, signal generators, wireless communication, wireless power transfer. This is present inside, and it transfers the energy using mutual coupling, which is wireless energy transfer, into recharging the battery present inside the device. Now this device is going in for clinical evaluations very soon. So we assume in another 2-3 years of time, this could really enter into the clinical usage in our country. Now the next important thing is the neural disorders not always cause movement disorders. If it happens in the brain, it creates movement disorders. What if it is creating issues in the heart? If it is creating issues in the heart, then we say it creates certain problems like sudden cardiac arrest. It may create fibrillation of the heart. Fibrillation means stopping of the heart. It arrests the heart. If the arresting of the heart happens, the patient collapses and the patient suddenly goes to a cardiac arrest. So you know that your normal heart beat is like 72 beats per minute. If the 72 beats per minute is going on irregular, then there are so many different conditions called tachycardia, brachycardia, and all. If this particular system can, if any system can be developed which can identify it much earlier before the occurrence itself, then the cardiac arrest and the sudden collapse of the patient can be avoided. So such a device is called implantable cardioverter defibrillator. It's another active implantable medical device, which is a battery operated device, which performs the cardioversion. Cardioversion means converting the fibrillation into a defibrillation. That means a polarized stage into a repolarized stage. So that is happening within the body itself by having a small device kept under the skin near to the shoulder, and then a set of wires will be passed through the brachial artery, which is the artery which is coming into the arms and provide supply blood supply to the arms. So we puncture and then deliver it. The cables are routed, and finally the cables are taken into the heart muscles, and the heart muscles inside the cables are connected into the muscles of the heart. So what it does is it provides direct current through the heart muscles and depolarizes the entire myocardium. Myocardium is a muscles which actually the muscles of the heart. So it depolarizes the myocardial tissues, and the heart attack problem can be reversed. If we could have it detected, there are certain algorithms present in this device which keeps on understanding the actual pattern of the heart rate. And if there is any small deviation, then it will find out that and then give the corrective action. AI, artificial intelligence, can play a major role in the future, because you may have hundreds and hundreds of ECG signals taken, and then the AI tool can predict when it is going to happen, and this device can deliver the electrical signals into the heart for making the corrections well ahead. So this is another device which is so important in sustaining the life of a person and creating a healthy living to a person. Now coming into the chronic diseases, pain management, cancer, diabetes, those devices are the another major issues in the top 10 list of diseases all across the world, and which is mostly for the 21st century because of our way of living. Our life standards have changed a lot. We are having a lot of junk foods. We are having a lot of issues on the exercise regime, on habits and all. Because of that, so many diseases are coming up. One is a diabetes, cancer, and disability. So how do you manage these devices? So these problems. So these problems can be managed by having a targeted drug delivery device. So a targeted drug delivery device has got a reservoir which can have the drug, and it will be kept within the body, and through a tiny tube, the drug can be given into the region of interest. So which are the region of interest? For diabetes, the drug will be insulin. It will be delivered into the intestine, peritoneal cavity. So there the insulin will be directly absorbed, and then it will immediately go to the bloodstream, and glucose will be maintained into the limits. If it is your spasticity or kind of cerebral palsy or some spinal cord injury or spinal cord related problem, then the small tube which carries the drug will be connected into the spinal cord. Then this whole device will be delivering the required drug called baclofen or morphine, which are pain management device managing drugs into the this spinal cord. Then another one can be for cancer treatment. Many organs get affected by the cancer. So there are so many chemotherapy drugs used for taking the organ back into healthy shape. But what happens is, if you're taking it orally or through IV, then the problem is side effects. Then you have to have a large quantity being taken to have a very small effect. So how do you avoid it? You can have a targeted drug delivery where very small quantity of drug need to be taken and will be given into the region of interest. Region of interest may be the diseased organ. So for example, here, a hepatic arterial infusion treatment, a direct delivery of drug, a cancer drug, to the colorectal cancer is being provided. Here, a small device will be kept within the body. It will be loaded with a specified cancer drug, and a small tube will pass into this hepatic artery, which will take the drug into the required organ and then cure the disease. So these are some of the new latest devices for the most modern life kind of diseases. So in this respect, we don't have these devices in the country so far. We have to work hard to develop all these devices. Again, SCTMST has played a major role in developing these devices. We had developed an implantable infusion pump, which is a very small device, which has got a portion called septum, where through which you can insert the drug, load the drug, and it has got a tiny tube which can be kept into the region, like in intestine or the spinal cord, or to the different organ which has got with the cancer. It can be recharged like with wireless energy technology. It can be refilled once in 3 or 4 months time. So no need of multiple injections, just injection 1 or 2 times a year. That is enough. Injection is very simple injection. You have to just refill the reservoir kept within the body. So this device behaves like an artificial pancreas. Active device acts like a pancreas for the case of diabetes management. It acts like a targeted drug delivery device in the case of a cerebral palsy or a spasticity. It acts like a pain pump in the case of a cancer for old age or palliative care situations. So these are all devices which are very critical, life-saving devices, which comes under the category of active implantable medical devices, which has got a battery operation, which has got a continuous recharging, which has got some programming required, which has got control actions required, which has got precise delivery and of electrical energy or drug or chemicals required, which need to be monitored by an external system outside the body and all. So this set of devices are very complex, are not available in our country. We are still working on it, developing it. Our whole community of biomedical engineers or electrical engineers, mechanical engineers could give their attention and focus on developing these devices in the country, because these are need of the hour. So let us slightly deviate from these complex devices into certain simple devices which are highly futuristic, which are not being developed completely in any part of the world. I'll take another 5 more minutes to finish that portion as well to make it complete. I request permission for that. So hope I can continue for 5 more minutes.
Yes, yes, sir. Yes, sir.
Okay, thank you. So another area which has attraction attention of the researchers all across the world is micro electromechanical systems. Now it has gone further down to nano electromechanical systems. This can really change the scenario of filtration in the case of a kidney. So you may know a patient having kidney trouble need to have a dialysis, and his life completely gets miserable when you have this dialysis done twice in a week in a hospital. What we can do in that, we can have a micro electromechanical systems based active implantable device which functions like an artificial kidney. So these are all silicone nanopore membranes which has got the filtration capacity similar to that of the kidneys. You could see here, these are all silicone membranes. There is a silicone substrate. It behaves like a artificial kidney. It can be kept in the place of the kidney, just like our kidney transplantation. This gets placed into the location of the kidney, and we connect the renal renal veins and the arteries. It communicates with the bloodstream and then filter it out, and the normal process of removing it happens there. So this is something which is coming out it's there in the research now happening on in a certain part of the world. And another one is intraocular pressure. Certain aged population have got their eyes being getting problems. I have read an article 2 days back in the recent edition of Friendline magazine that in a particular hospital, certain patients have been treated with eye disease, and then they had to suffer with being blind later. So modern technologies are required to avoid such kind of situation. So what we can do on that, we can have this micro electromechanical systems based medical devices which can actually keep on monitoring the pressure and the visibility point of view, the visibility of the eyes, the sensory things of the eyes, and then communicate with external devices and understand on the progress of the disease, or make corrective actions at the time it has been crossed the limit. Similarly, continuous glucose monitoring. People suffering with diabetes need glucose monitoring continuously. What can we have something kept inside our skin, inside our body, very small, which will keep on communicating with an external mobile phone? Then that gives you information about real-time glucose present in your body. These are all revolutionary if it happens. I urge the students and those who are listening to this talk to pay your attention onto these areas where you can contribute. You can work on these areas. Another upcoming area is micro medical robots. Tiny robots which can go inside your body, can even scan, can even measure, or can have dimension analysis, or can visualize the internal regions and then send the image back to the outside world. These are tiny propelled robots for variety of application, including you can remove a clot, molecular level management inside cells. This can also be happened. So a lot of polymers, a lot of very small metallic structures have been developed, which can navigate through the bloodstream and then go into the region of interest and then make corrective actions. You can see in situ here a picture of a tiny propelled robot for creating small incision, that means small wound, and then deliver the drug into the organs. So these tiny objects really play a major role in the future for targeted or kind of micro medical robotic drug delivery systems. So what are these micro robots? Micro robots are very miniature active implantable medical devices which gets power from not only with electrical but from so many other sources. It can be chemical, it can be with a swimming action, it can be with a magnetic gradient, or it can be bio-hybrid propulsion. So you can see here how it functions. The movement can be produced by kind of expelling certain chemicals from one side to the other side. There will be a force. It's a very simple rocket technology. Chemical propulsion. Chemicals will be released from one end so that you get a propulsion to the other end. Another one is called swimming. So you can have a helical swimmer, a very small structure, very small. These are all micro. I should say the size. The size is like 20 or 30 to 50 micrometers. It's like a 1/5 of the size of your hair. So that size. This small spring-like structures rotates. When it rotates, it gets a one-directional force, unidirectional force. This force will help it to move in one direction. It can be like a kind of a wings of a bird. It's called cilium, artificial cilium. You would have seen fish moving. Now, the fish has got a particular pattern for its wings to move. So the same movement can be replicated so that it moves in one direction. There can be another one called magnetic gradient. That means there will be tiny magnets kept within this micro robots, and from an external magnet, if the external magnet moves, the tiny magnets also move within the body. So in that way also you can take it into the region of interest and do some activity. There can be so many electrically powered systems. When you say electrically powered, it is not directly connected. It works with the energy obtained from an electromagnetic pulse. So what are the different types? There can be rotating fields, where a rotating type of an electromagnetic field will be produced, and that induces certain force onto the system. It's something like, you would have seen Faraday's laws of electromagnetic induction. I still remember how Kasim sir teaches us on the electromagnetic field theory and how a motor functions. This really helps in creating micro robots. But only thing is, it will not be like our conventional motor. It will be like a completely unconventional, non-traditional approach. You have to get this particular, but the physics principles have to be deployed. You have to learn, understand the physics principle, and then do this activity. Oscillating type field gradients. These are the different types of electromagnetic configurations which can be used for making this micro robots. Okay. Now we have discussed a lot about the devices in the active implantable domain, but why people are not making it so often? No, why? What is the problem? I think the Zoom has lost. Is there any problem on the Zoom?
We can see you. Only thing is the screen is not visible.
Yeah,
The
actually,
slide is not visible.
The Zoom has come out. Is there any time limit for the Zoom?
No, no, we are able to see your email now. You can just start representing that. I think it should be okay.
Okay, I'm just. Okay, so I'll just continue. So what are the major challenges? The major challenge is our body. There is a temperature limitation. You cannot have more than 37 degrees Celsius for our body. So the maximum allowed extension of the temperature is like 2 degrees Celsius. So 37 degrees Celsius is the maximum which you can do. Now it is visible, I believe.
Yes, it is visible. We can make it full screen.
Right.
Thank you. Yeah, it's perfect.
Okay, so human body is a highly complex living system. It is completely electrolytic. That means it's completely corrosive in nature. There's an unparalleled immune system. You know that we all now still also not going to a hospital, and then we are not confident in getting an injection for TT. Why? Because we are not sure about the needles, how the needles have been manufactured. So because we have got a very high unparalleled immune system, any foreign object going into the body, it gets simply rejected. It is self-destructive also. It try to destruct the whole environment. That's why we are getting fever. You know that the COVID, the majority problem is because of our immune system. It distracts the whole body to get rid of these viruses. It rejects any foreign object. That's another major issue. You cannot simply keep any object inside your body and then say it works forever. No, completely in another 2 to 3 days time, infection will come. Within 7 days of time, the thing will get rejected. Earlier, you would have heard about our grandparents telling, if there is a small prick by a tiny thing, then automatically the body will reject it and it will come out of your body through pus, because it happens really because of the unparalleled immune system. The thermal limit, as I said, 37 plus or minus, sorry, not minus, plus 2 degrees Celsius. Minus is there called hypothermia, that is not coming in this particular domain. Electrical energy delivery is kind of impossible, because you can have direct delivery through cables, but how do you sustain it? No, you cannot do that, because infection is a real problem. You need to take a wire inside the body, and it's very difficult to maintain it for a long time. But you need wireless energy transfer. But wireless energy transfer, to so far, it's only for direct contact. That means you have got a coil, you have got another coil, direct contact. That means the coils will be present within a mobile phone, another coil will be there. Very small gap is there. But you see the human body, it's not like that. Human body is always moving. So this coil, it's always moving. Your fat deposit will always change. So that means the gap keeps on changing. These are all factory developed. You cannot have in situ adjustment on the system. So all factory developed, all maintained in a clean room, manufactured in a clean room environment. So, but when it is deployed, it will be deployed on a patient of different sizes, different ethnicity, different body shape, different countries, different kind of fat thickness. So you need to have lateral tolerances. You need to have the changes due to respiration. You need to have different adjustments due to your body movements. You're sitting, standing, walking, lying down. Every time this energy transfer should work. So because of that, it is totally kind of impossible. Then another thing is the age has not, the disease has not age limit. You can get any kind of disease to a newborn baby. The same disease can get to an old person also. So you cannot have a device being developed with different specifications. You need to have one specification developed and need to be put in different type of body, different type of patients. So these are the many challenges. So even if we have all these challenges, so many developments has happened, which has to go through so many type of evaluations, which contains biocompatibility evaluations. We need to see whether the device is compatible to the blood, tissue, whether it is causing any toxicity to the body, whether it is any heat producing, thermal problems and all. And also so much of safety testing has to be done. I would categorize the safety testing into 3 different regions, like mechanical testing, electrical testing, and electromagnetic compatibility testing. These are the list of tests to be conducted for doing a safety analysis of the device, starting with the mechanical to the electromagnetic invisible radiations, what it does on this particular device. So you need to have a mechanical direct contact problems, you need an electrical contact issues, also some radiations, how it causes the problem. So the another major challenge is you cannot simply evaluate the device on a table. You need to evaluate it through a human environment. But human environments are not easily accessible. You need to prove the technology first and then go to the human environment. If a failure happens in the human environment, again you have to come back and then do the enter exercise once again. So because since it is too tedious and not, obviously not happening everywhere, you need to have an interface. That interface is a human equivalent model. So the human equivalent model is called animal evaluation or animal trials. So animal trials mostly will be done on sheep or a pig, where the position of the device will be like the device dependent. 3 to 6 months time, you'll be observing the animal which is put with this particular device, and later the animals will be evaluated with understanding what has happened to this particular device and to the animal as well. That there will be a risk to benefit analysis will be conducted, and benefit will be assessed, risk will be assessed separately, and then finally going to the human trials. So this is the battery of tests and the battery of evaluations, and the way an active implantable medical device, even if it comes into the human use, will finally will take. This is a journey it has to take. Because of this, in India, very less number of devices have been totally developed. Even if something has been developed, it would have been taken from somewhere else and then manufactured here, not the technology being developed. In a CTMST, we in the last 10 years time, we have shifted our focus into active implantable medical device. Some of the devices which I have shown today in the talk are being developed, and animal trials are going on. So with this, I thank you for giving the opportunity to talk before you on the complexity of these devices, the challenges. I hope this gets benefited, and you may be able to do make some contributions in this. Thank you very much.
Thank you so much, sir. Now it's a Q&A session. If you have any doubts, you can ask.
Dear Sharath, thank you for the informative talk on this equipments and our human system. And really, I am happy that you have grown from electrical engineer to a biomedical engineer in a short span of time in an excellent manner. And can you slightly or briefly just give an thought of your transition?
Actually, I started my journey from electrical engineering. Yeah, I started learning electrical engineering from you, sir. You are my advisor. You have taught me electrical engineering, and from there, after my BTech from TKM College of Engineering, I got campus placement in Larsen and Toubro. There, I worked on electrical systems and especially on the cloud mechanisms. 15 years back, it was the first time a cloud computing-based systems on real engineering has been deployed in our country. So I was fortunate to work a little bit on the cloud-based management of the real electrical systems, ground systems. I started my career in that, and then later I did my post-graduation from National Institute of Technology, Calicut, where Dr. Ashok was my mentor, and I worked on magnetic bearing and developed a completely active magnetic bearing systems in 2007-9 period under Dr. M.L. Joy. Then after that, I joined in Amrita University, Coimbatore as assistant professor, worked there for some time. From there, I shifted to, from there actually started my work on healthcare because I have got some ideas, and then from there slightly shifted into the healthcare segment. Then shifted to G Healthcare, General Electric Healthcare segment, where I worked on X-ray machines and MRI machine technologies. That totally changed my perspective of engineering, where I could see real engineers and engineering and people working on complex systems, very complex systems. And it came to my mind that why our Indian engineers are not really working for the India, but not are fully working for other countries. That was in my mind, and I got an opportunity at the same time. Got an opportunity, or got a call, got to know about an opportunity in SET chemistry, where similar kind of activities were going on. Whatever the complex works were happening in GE, very similar complex operations and research were happening in SET chemistry. But GE is a very big name, but SET chemistry is totally unnoticed. But when you go into the depth, the value which SET chemistry has created is much, much, much more because of the developments which it has done here. So I made up my mind to shift to SET chemistry. There I got a fellowship called Chitra High Value Fellowship. Then we had to work for 3 years and prove that you are worthy enough to be taken by SET chemistry. And then there was a faculty opening, and it was a general recruitment open call, and I got into the scientist D position. And in last 10 years, I've got promoted into scientist F, where I could work on under Dr. D.S. Nagesh and Vinod Kumar V, who is very active in EMBS and IEEE. We three are a team working on active implantable medical devices under the able leadership of Dr. D.S. Nagesh. We have worked on all the technologies which I've shown today in the talk, starting with the LVAD, infusion pump, and my team colleague, Mr. Jidin Krishnan and Dr. Murli Dharan CV. He works on deep brain stimulator, and we are also fortunate to be a part of that team as well. So means we are working on this implantable medical devices for 10 years now. So this is my change, the transition from an electrical engineer to an interdisciplinary biomedical engineer.
Yeah, okay, great. And so now I hand over the mic to other participants, please. Any doubt, please?
Sharat sir, you can see the chat box.
Oh, is it? Okay, how can we protect biomedical implants from cyber attack? Savan is a very good question. Actually, I do not have a direct answer for that. We have to have a lot of protocols to be put in place in the microprocessor coding onwards, the algorithm development onwards, on protecting the functionality of the device. We are also having a deep thought on how this can really be implemented. As of now, there are only very or no cases at all regarding the cyber attacks on this implantable biomedicals. But certain misleading videos and misleading informations have come out on the internet, which might have prompted you to ask this particular question. But even though this is not a risk today, we all believe that maybe 10 years down the line, 20 years down the line, once the active implantable medical devices take over, there will be a serious issue. What we have to do is very carefully, you have to develop the algorithm, and it will be better if you have dedicated controllers for connecting to the devices, not a generic controller. So a generic controller like a mobile phone. So sometimes you have a mobile phone. Most of the time, mobile phones are there with you. The mobile phones will be the easiest point of control to the medical device. But the problem there is the mobile phone can be hacked, so the controller can be hacked. But what if you have a dedicated controller? Then the dedicated controller, there is a very little chance of having a hacking done on the dedicated, unless otherwise you get it. Maybe you get it, it is possible. But otherwise, a very little chance. But the problem associated with that is you will be still 30 years back. That means you will be still having another controller. That controller will be so dedicated, and if you misplace it, or if it is stolen, or if it is not readily accessible, then that will be an issue. So certain new kind of advanced research is happening in other parts of the world, where you have got implanted controllers as well. You have only access to it, or your clinician is only having access to it. So like you have got an Apple Watch nowadays, no? Apple Watch will be with you. Assume there are certain devices just within your skin and still controls it. So such kind of devices are there in the research. Probably that will help. And another question is, what factors are being considered in the manufacture of medical implants? As I said above, one is it should not be no, because it's an electrolytic environment, so the corrosion, that's one factor. Second factor, these are all I'm telling about the manufacturing part of it, but on the technology aspect there are so many major factors, those factors need to be solved to make it into a medical device. That's why I'm skipping that. So in the technology aspect, you need to have no thrombus, very less the hemolysis, that is breakdown of blood cells, should have a long or a kind of reliable operations possible. Then it need to be worked on a corrosive environment, so no corrosion or very little, or it should not be there. And then the metal should have extremely superior surface finish, which is very difficult to achieve. So you need to have there are certain coatings so that this coatings behave like a mask to the metal, and the blood or your tissue will seed like the ordinary epithelial cells, the ordinary tissue cells. So in that way, you may be able to mask the device. Then infection should not be there. So you need to be able to provide certain so many other kind of design approaches so that infections can be completely controlled. What is a common risk of medical implants? That's another question. The major problem is blood damage and blood clot. These are the two major things. Because infection and all, you may be able to control with so many practices, medical practices, whereas the design determines whether the blood gets damaged or not. So see, something like the blood is an organ, no, it is a living tissue. You say the LVAD, it's a pump. You take your mixer grinder is also a pump. Your water jet pump is also a pump. Your industrial pumps are also pumps. But all these pumps are not pumping living cells. But whereas the pumps and all those devices which I have shown in the today's presentation, they are going to handle living cells. So the living cells, any small damage on the living cell, they'll actually make damage to the other cells also, because it's an immune response. So so that need to be avoided. So hemolysis, we call medically, it is called hemolysis, or the blood damage. So the blood damage need to be highly controlled. Another one is the clotting of the blood. The clotting of the blood happens whenever there is a low velocity of blood in your entire system, or stoppage of blood in your system. Within minutes, the blood clots. If you have a wound, within seconds the wound closes, like because of a clot. So the same clot, if it happens in your body, then it migrates into the brain and then stroke will happen. If it migrates into the heart, then heart attack will come, or a myocardial infarction will come, heart failure will occur. Those are the most common risk associated with the medical implants. Any more?
Thank you so much, sir.
Thank you.
Now, I would like to invite Advaita from Muslia College of Engineering, Trivandrum, for proposing vote of thanks.
Good afternoon, one and all present here, Honorable Chief Guest, Mr. Sharath S. Nair, and the participants. It is such a honor for me to get the opportunity to thank all the dignitaries and participants. On behalf of IEEE EMBS Kerala chapter and the flagship event, Ignium, to all esteemed delegates of the webinar for their presence and contribution to make this webinar a great success. I extend my gratitude to our Honorable Chief Guest, Mr. Sharath S. Nair, to take out time from his busy schedule to grace the event. Thank you, sir, for your inspiring and encouraging us with your words. A special thanks to Dr. B.S. Manu, sir, Chair IEEE EMBS Kerala Chapter, Mohammad Qasim, sir, Vice Chair of IEEE Kerala Section, and Dr. Jayashree ma'am, our Student Activity Chair, for her concerned support to make the webinar successful. And also thanking the Faculty Advisor of Muslia College of Engineering and Modern Engineering College. I must thank the organizing team and volunteers for working hard for the past few days to make this webinar successful. Thank you all.
Thank you so much.
Yeah.